welcome to the Deep Dive. Today we're really zeroing in on, well, a pretty fundamental question in AI, isn't it?
It really is.
How do these incredibly powerful large language models, these LLMs, how do they actually learn to reason? We see what they can do, it's amazing, but are the ways we're teaching them hitting some kind of wall?
That's the big question, yeah. Are current methods sustainable for the complexity we want?
Exactly. So our mission for this deep dive is to explore a really fascinating, maybe even groundbreaking new approach. We're looking at a recent paper just submitted May 26th, 2025.
Relatively fresh off the press.
Right. It's titled Learning to Reason Without External Rewards. The authors are Xuandong Zhao, Ziwei Kang, Eaosong Feng, Sergey Levine, and Dawn Song. And this research, well, it seems to really push how we think about AI learning.
It challenges some core assumptions, definitely.
So what can you expect today? We're going to try and unpack how LLMs might develop these complex reasoning skills, but not from, the usual human-provided answers or reward signals.
Right, not the typical labeled data approach.
No, it's something much more internal, intrinsic. Get ready for maybe a bit of a shift in perspective on what real AI autonomy could actually look like.
It's definitely an important distinction to make, and I think to really get why this new paper is significant, we should probably first talk about the current standard, right?
Good idea. What's the usual way?
Well, for a long time, let's say the dominant method for training these models in complex reasoning tasks has been something called reinforcement learning with verifiable rewards. RLVR for short.
RLVR.
And look, it's effective. It definitely works. But its Achilles heel, really, is that it leans so heavily on costly domain-specific human supervision.
Meaning someone has to constantly check the AI's homework.
Sort of, yeah. You essentially need a constant stream of human-labeled data or verified correct answers, which is, well, it's expensive to create and incredibly time-consuming.
Right.
And that bottleneck, that dependence on external verification, that becomes a huge hurdle when you start thinking about scaling these things up massively for the real world.
So it's a bit like training an Olympic athlete who absolutely needs their coach right there, second by second, giving precise feedback on every single tiny movement.
That's a pretty good analogy, yeah.
It works great for one athlete, maybe even a small team. But what if you need to train, I don't know, millions of them all at once? That human coaching just doesn't scale.
Exactly. The human element becomes the limiting factor. And that's precisely the challenge this paper tackles head on. They introduce this new framework, reinforcement learning from internal feedback, RLIF.
Okay. RLIF. So internal feedback. How does that work?
The core idea is that this approach allows the LLM to learn from what the authors call intrinsic signals instead of looking outwards for rewards or verification.
It looks inwards.
It looks inwards, exactly. Crucially, this means no external rewards are given, and you don't need that mountain of human-labeled data. The model is essentially learning from within itself.
Wow, okay. That sounds like a massive leap.
Yeah.
But how? How does an AI know if it's doing well if there's nothing external telling it, yes, that's right, or no, that's wrong?
That's the million-dollar question, isn't it?
Seems like it. The paper proposes a specific method for this RLIF framework, right? Called Intuitor.
That's right, Intuitor. And the mechanism they describe is, well, it's really quite ingenious. Intuitor uses the LLM's own confidence level.
Its own confidence?
Yes, what the authors specifically call self-certainty as its only reward signal.
Its only reward. So it's basically rewarding itself for feeling confident about its answer. How does an LLM even measure self-certainty in a useful way?
Yeah, that's a great question. It's not feeling confident like a person does, of course.
Right.
It's more technical. Often it leverages the model's internal workings, specifically the probability distributions it assigns to its own outputs. So when an LLM generates, say, an answer or a piece of code, it's calculating probabilities for each word or token it produces.
Okay. Like how likely it thinks the next word should be.
Exactly. And if an entire sequence, a whole answer, has a high overall probability, if it's coherent and internally consistent according to the model's own calculations, the model is essentially more certain about it.
So it's a quantifiable mathematical kind of certainty.
Precisely. It's a quantifiable internal assessment. And that becomes the reward signal. Intuitor then takes this internal score and plugs it into an existing reinforcement learning framework. specifically something called Group Relative Policy Optimization, or GRPO.
GRPO, what's that quickly?
GRPO is basically a powerful technique where the model learns by comparing different possible actions or outputs against each other relative to the group performance. Intuitor just swaps out the usual external rewards in GRPO.
And puts in these self-certainty scores instead.
Exactly. And that switch allows the whole learning process, the whole optimization, to run purely on internal feedback. It becomes unsupervised.
Okay, that's fascinating. So it's learning by comparing different answers it generates and favoring the ones it feels most certain about based on its internal math.
That's the core mechanism, yes.
So if this internal feedback idea, this Intuitor method, is really as revolutionary as it sounds, the proof has to be in the pudding, right? The results. Did they test it? What did they find? Did it actually work?
They certainly did test it, and the findings reported in the paper are quite compelling, actually. First off, they found that Intuitor could match the effectiveness of the standard externally rewarded GRPO on traditional tasks like mathematical benchmarks.
Just matching it is pretty significant, given it doesn't get the external answers.
It really is. It shows the internal signal is strong enough, at least for those kinds of problems. But here's where it gets, I think, really interesting. The paper highlights Intuitor's superior generalization.
Superior generalization,
Uh-huh.
meaning it performs better on tasks it wasn't specifically trained on.
Exactly. Better performance on out-of-domain tasks. And they specifically call out its performance in code generation.
Wow, code generation. That feels like a really tough test case.
Yeah.
It's so structured. Usually you need very precise feedback, like, does this code actually compile and run correctly?
Indeed. Code generation typically demands that kind of objective, verifiable feedback. You need to know if it works.
So how did Intuitor manage?
Well, this is the most striking part, I think. The paper states this performance, including the superior generalization in coding, was achieved without requiring gold solutions or test cases.
Wait, without gold solutions, no predefined correct answers, no test cases to check against.
That's what they report. Think about that. The model learned to generate effective code and, crucially, generalize that skill based only on its internal assessment of its own generated solutions, its own self-certainty.
That changes things, doesn't it? If that holds up, it fundamentally alters how we might train AI for complex, creative, or maybe even open-ended problem-solving tasks, where there isn't one single right answer.
It really does. It opens up possibilities. So what does this all mean for you listening and for the broader field of AI?
You have the bigger picture.
Well, the author's work here, it demonstrates quite strongly that these intrinsic model signals, this self-certainty, can be effective drivers for learning. And across different types of tasks, different domains.
So it's not just a theoretical curiosity.
No, it seems practical. And if we connect this back to the scalability problem we talked about earlier.
Right, the bottleneck of needing human feedback.
Intuitor offers a potentially scalable alternative to that traditional RLVR approach. Because it doesn't need the constant external verification.
Which could be huge.
It could be huge. This is especially vital, you'd think, for developing autonomous AI systems. Systems where those verifiable rewards are just unavailable or impractical to get.
Like what kind of situations?
Oh, imagine AI systems deployed in really challenging dynamic environments. Maybe deep space exploration where communication lag makes real-time feedback impossible. Or managing complex, unpredictable chemical reactions in a lab where you don't know the optimal outcome in advance.
Or even things like drug discovery, where finding the ground truth takes a long, long time.
Precisely. Areas where maybe the ground truth isn't immediately clear or easy to verify, Intuitor suggests a pathway for AI to learn and adapt continuously in these sorts of frontier domains, relying on its own developing understanding.
That's pretty profound.
And another point, just on practicality, they've actually made the code for this research publicly available, which is great. It reinforces that this is practical, potentially replicable research others can build on.
That's always good to see. Okay, so let's try to recap the core idea here. We've been exploring this new frontier in AI where large language models, LLMs, can potentially learn complex reasoning.
Not from external rewards or answers.
But by essentially tapping into their own internal self-certainty, their own calculated confidence in their outputs. It's almost like they're developing an inner compass to guide their own learning and improvement.
That's a good way to put it, an inner compass. And it really forces us to consider, well, what does it mean for an AI system to learn autonomously, to judge its own performance and refine itself without constant human handholding?
Yeah, and how might that change the AI tools and systems that you interact with? Maybe sooner than we think.
Yeah.
Especially in those areas where, like you said, human supervision is just impossible or impractical.
The potential applications are quite broad if this pans out.
Definitely. And maybe for a final thought, something to kind of chew on after this. If AI can learn complex reasoning by essentially trusting its own internal self-certainty,
Yeah.
what does that imply about intelligence itself?
Ooh, that's a deep one.
Right. Both artificial intelligence and maybe even our own human intelligence. Does it hint at some deeper, maybe universal mechanism for understanding and learning that doesn't always need that external, you got it right, stamp of approval? Maybe learning can happen just by striving for internal coherence and confidence.
It certainly makes you wonder about the fundamental nature of learning and knowing, doesn't it? A fascinating question to ponder.